We are now at a point where it makes sense to incorporate matrix arithmetic. So far, we've only been using matrices to perform Gaussian elimination and to solve systems of linear equations, but that's not all matrices can do. Matrices can keep track of data. For example, let's suppose that this data table I have here shows the prices to attend, let's say, a play across 2 different days for 2 types of tickets. So for instance, if we want to go to a Saturday event, we have to decide whether we want to purchase general admission or VIP admission, and we can see it's going to cost us $5 more to have VIP admission. When we move over to Sunday, all the prices go down a little bit. Maybe not everybody is interested in attending on a Sunday. People would rather go on a Saturday date night, and so we see there's a bit of a discount between the two admission costs. Now, there are really 2 types of operations that we are going to investigate here, and those are scalar multiplication and addition / subtraction of matrices. So the first thing I can do here is I'm going to strip this table of its labels and create a matrix called A that's just going to contain the values without units. This is a very operational thing to do because now we have simple numerical data on which to operate. So we have this notion of scalar multiplication. What we can do to a matrix is we can scalar multiply a matrix by some scalar. So for instance, if I wanted to take 2 times A, well, that's identical to saying 2 times the components of the matrix. So by definition, we're going to, just like we would with vectors, scale all of the components by the factor of 2. So 2 times 10, 2 times 5, 2 times 15, and 2 times 10. So what would be the meaning of this type of matrix? Well, maybe this is the company finally deciding to double its price. Maybe the demand has gone up, and when they were a startup, they could charge less, but now that they have more demand to attend their shows, they can charge $20 for a general admission ticket on a Saturday night and $30 for a VIP admission on a Saturday night. So we could imagine this to be new costs after doubling prices. Now we could also say we want to increase the prices by, let's say, 2%, and we could take something like 1.02 times A, and that would be 102% of the values, which means that we would get back not only the original, say, $10, but we would also get this extra 2%. So the first component in here would be, say, 12, and then we could do the rest of them in this similar fashion, and that would indicate a 2% price increase. So we can scalar multiply. Of course, our scalars don't have to be the scalars that we could use here could be any real number. Any real number. So remember, that means real number. So the way I will go ahead and write this is that C is going to be some scalar, some constant, and it's going to be an element of the real numbers. So this just means C is a real number, or C belongs to the real numbers. Now we can also take a matrix with another matrix and add the values together. So for instance, if we created a new matrix called B, and perhaps this B matrix represents some price increases. So maybe we don't want to adjust all the prices by some variable amount, since percentages will result in different amounts being applied to different values. We might say across the board we want to increase general admission for both of the days by $1, and maybe we want to increase VIP for across both of the 2 days by $2. So it seems intuitive that if this is a 2 by 2, that if we want to add another matrix to it, it must be the same size. After all, if they're not the same size, then there's going to be some elements that don't get added to any other elements in the second matrix. Now, if we wanted those missing elements to be zeros, then we should adjust the size of the matrix so that it has zeros in the places where we want to, say, add 0 to the first matrix. So A plus B the sum of these two, as long as they are the same dimension. So for addition, probably should have written that first. So we also have addition and subtraction. For this to take place, addition and subtraction require that both matrices be the same size. And maybe for now, we'll just go ahead and say that both matrices are of size m by n. So if A is m by n, the only way we could add or subtract B from it is for B to also be m by n. Okay. Again, if the sizes are different, now m and n could be the same. It could be a 2 by 2, but by using m and by using n, we're just indicating they don't have to be square, meaning same number of rows and columns. They could be 3 by 7 plus a 3 by 7. So addition takes place much in the same way we would expect. I'm just going to go ahead and write the matrices out here, and we're going to add to that the matrix containing 1, 1, 2, 2. So we're going to do element-wise addition. This value here and this value here will produce the new first row, first column element of that matrix. So we could say that on a Saturday, now to get general admission, you're going to pay $11. And on Sunday, it used to be $5 for general admission, but now it's going to be $6. And then here on Saturday to get VIP, it's now going to cost you $17. And to get VIP on a Sunday, it's now going to cost you $12. Now, whether we add or subtract, it doesn't matter. Subtraction would take place in exactly the same way. We often bundle addition and subtraction as just addition. And that is to say that what we could think about subtraction as, subtraction is really just addition with a scalar of -1. So in other words, A minus B, so A minus B is equal to A plus -1 times B. And so now we're combining we're not only doing scalar multiplication, but we're also doing addition of these matrices. And you may recall that with vectors, we were able to scale vectors and add them together and put them together tip to tail. Unfortunately, that meaning is not the same for matrices because now we're not living in vector space anymore. We're living in this thing called matrix space. So instead of saying that we're in R2, we're in R, say, 2 by 2, or the space of all 2 by 2 matrices. But that's not really relevant right at this moment. So we often just say we have scalar multiplication and addition because that suffices, and subtraction is really a redundant saying. To formalize our intuition a little bit more, we often like to think about general situations. So if A is any m by n matrix, and what we mean by that is we're just going to have elements in here. So this is row 1, column 1, so we're going to call that little a sub 1, 1. That just means that that's a number, that's not a whole matrix. Little a is just an element inside of the matrix called big A. And oops, I called that row or column 2 instead of column 1. And now if we move to the second element, that's a sub 1, row 1, column 2. So where we say row and then column. Now this is going to go on, right? Because we have n columns. We have n columns. And that means that we're going to have, in the first row, we're going to have an nth element inside of that row. And now we could go on, we could do the same thing for the second row, A21, A22, all the way up to A2n. Now this is going to have m rows. So that means the mth row will be AM1, AM2, all the way over here to AM and the nth column. We're now column n. And so we'll just put some dot, dot, dots here just to indicate this this could be any size. It could be 1,000 by 300. And as long as B is the same size, and I'll spare some of the detail here. We'll just say B11 all the way up to B1n, and B21 all the way up to B2n, all the way down to the mth row, first column, all the way over to the mth row, nth column. And as long as these are the same size, then we can kind of write this general statement that A plus B, or A plus or minus B, we could put a minus there as well, is just going to be the sum of the two components, A11 plus B11. So that's this component plus this component, all the way over here to A1n plus B1n. And in a similar way, we could continue to write in this bottom component here, with this bottom component here, AM1 plus BM1, all the way over to this final component here, AMN plus BMN. And so this is the more formal definition of matrix addition. And the reason we share this is because when we're trying to reason through properties, we have to come back to some formal definition of what it means to add two matrices. And this is as formal as we can really get. Here we were illustrating with some numerical examples. Well, that brings us to the final phase of some properties that scalar multiplication and matrix addition have. And so here are some of those properties. Here, let's go ahead and define three matrices, A, B, and C. And they're of the same size. That's critical here, because if they are not of the same size, then we may not be able to necessarily add them. And let R and S be scalars. So R and S are just some real numbers. Could they be 0? Sure. It could be any real number we want. Now, the first property here says that if you add two matrices, that you're going to get the same result if you add them in the opposite order. And this may seem trivial at first. You might just say, well, this is the commutative property, but that works for real numbers. But how do you know that works for matrices? Matrices are not numbers. Matrices are collections of numbers. To establish some intuition behind why this is true, we just have to come back to the top and say, well, by definition of matrix addition, we just add the components, A11 plus B11. Well, if we reverse the two matrices and added them in opposite order, then we would be adding B11 plus A11. And since A11 and B11 are just two real numbers, well, we already know that real numbers have the property that if I take 2 plus 6 versus 6 plus 2, I get 8 either way. And that allows us to come back here and generalize our findings. Now, the second one is saying that you add three matrices together, it really doesn't matter which two you add first in the sequence. You could do A plus B, calculate that, and then add C to that. Or you could even add B plus C together and then add A to that. And this is often called the associative property. And once again, we can reason through this by saying, well, all we're doing when we're adding matrices is we're adding components. So if I add, let's say 3 plus 4 plus 5, if I add 4 plus 5 first, if I add 4 plus 5 first here, I'm going to get 9. And if I add 3 to that, I'm going to get 12. If I take 3 plus 4 first, I get 7. If I add 5 to that, I get 12. And so as long as we can reduce our thinking to real numbers, then we can take advantage of all the properties that we know of. Now, because these are matrices and we're just adding elements, it's totally fine. And it works because of the fact that real numbers work the way they do. Now, what is this weird A plus 0 thing? Well, 0 is a matrix. So 0 has to be the same size as A. So if A was to be 1, 2, 3, 4, it doesn't matter what components, but if the second matrix contained all zeros, then intuitively, if you add 0 to all the components of A, you're going to get 1, 2, 3, 4. So nothing magical, but it introduces what we call the zero matrix instead of just the zero vector like we've seen before. Now we have a distributive property. Now remember, R is a scalar, so we're saying here that if we add A and B first, and then take that result and multiply it by R, we would get exactly the same answer as if we distributed r and we multiplied, scaled a by r, and then scaled all the elements of b by r, and then added those two results together. We're going to get the same answer. Now, I'm not going to do the whole thing here, but let's just look at the first component of a and the first component of b. And then it has a bunch of other components in here, but we're just going to focus on just this one property. So if I take r times the quantity a plus b, what I'm going to get is, well, first of all, if I add these together, I know that the result will be a11 plus b11. And then, of course, all the other elements will get added together in that same way. And then if I take that result and multiply it by r, well, that's going to give me r times a11 plus b11. And wait a minute, a1, this is now dealing with real numbers, and we know that the distributive property applies to real numbers. So this is the same thing as saying r times a11 plus r times b11, and all these elements will be the same, r times a21 plus r times b21, etc. Now, if we break this back up into two matrices, r times a11 plus r times b11, and all the other elements in there, and then, oh, wait a minute, if they all have a factor of r, then I can factor out r and write this as r times a11 plus r times the matrix containing b11, etc. And wait a minute, this is just r times a, and this is just r times b. And we can see that all of these things are equal to each other. And so we can use that type of reasoning to establish this property. We won't go through E and F. E is just saying that if you have two scalars that are being added together first, you can actually sort of scale r by the first factor here, and you can scale a by the second factor here, and then you can add them together. And that's not extremely commonly used, but it might be helpful if one of these were an unknown and you needed to leave it as something like x plus 2. And then just if you have two scalars here, whether you multiply them together first and then scale a by that product, you're going to get the same answer as if you scale a by one of the two factors and then scale that result by the remaining factor.